For roughly $100,000 of compute time, an AI model successfully degraded the security of a post-quantum cryptographic algorithm known as HAWK-256. The expected attack cost to recover a key was mathematically slashed from 2 to the power of 64 down to 2 to the power of 38. The agent responsible for this cryptanalysis was Anthropic's Claude Mythos Preview. HAWK is not an obscure target. It is a third-round candidate in the National Institute of Standards and Technology's competition to define the next generation of cryptographic protocols capable of surviving attacks from quantum computers. To maintain its promised level of security against this new attack vector, HAWK's designers must now double their required key sizes. Doubling the key size immediately neutralizes the algorithm's primary advantage. It was designed to be an attractive, lightweight post-quantum option, and expanding the key footprint makes it impractical for many of its intended use cases. Standard software vulnerabilities almost always stem from implementation errors. A programmer mismanages memory and accidentally leaves a buffer overflow in a cryptographic library. The underlying math is secure, but the human code is flawed. The model did not find a coding error. It discovered a geometric flaw in the foundational mathematical algorithm itself, successfully automating high-level cryptanalysis. To achieve this, researchers placed the model in a semi-autonomous, multi-agent harness, where it operated for 60 hours, equipped with access to computational tools and existing cryptographic literature. Working as a pair, the agents evaluated multiple vectors. The first worker agent actually rejected this specific attack path as infeasible, but the second agent continued pursuing the logic until it found a way to exploit it. HAWK secures data by relying on a complex structure called the lattice isomorphism problem. To break the encryption, an attacker has to solve the mathematical equivalent of a vastly complex, multi-dimensional maze. This animated diagram represents that n-dimensional lattice. The AI searched this geometry and discovered a specific, unexploited symmetry known as a nontrivial automorphism. It is a subtle geometric weakness embedded directly in the lattice, one that expert human reviewers missed over a 2-year scrutiny period. By exploiting this automorphism, an attacker can execute a drastically faster enumeration attack, bypassing large sections of the mathematical problem. This bypass causes the effective key size to collapse, erasing a massive portion of the algorithm's defensive strength. Because the attack still requires exponential time, it remains computationally impractical against larger keys. However, it completely breaks the baseline HAWK-256 implementation. Using artificial intelligence to review complex specifications is no longer a theoretical exercise. The models can actively dismantle years of careful human cryptographic design in a matter of days. The researchers then pointed the model at a heavily scrutinized academic variant of the advanced encryption standard, specifically a 7-round version of AES-128. The AI initially refused to engage. It output text claiming that AES was the most heavily studied block cipher in existence, and that finding a new cryptanalytic improvement was impossible. The human researchers had to explicitly prompt the model, instructing it to operate as a top-tier researcher and to actively pursue genuinely novel and difficult mathematical findings. Over the next 3 days, the AI generated more than 1 billion output tokens, autonomously proposing, testing, and refining hypotheses. This schematic shows a standard framework for attacking reduced-round AES, the classic meet-in-the-middle attack. The attack works by trading computational time for storage space, calculating massive amounts of intermediate steps, and storing them in a centralized lookup table for rapid reference. The known bottleneck occurs during a phase where the attacker must blindly guess 256 different values and check each against the lookup table. To bypass this, the AI invented a highly sophisticated fingerprinting algorithm. It named this technique the Möbius Bridge. The Möbius Bridge operates by generating a fingerprint that remains mathematically invariant to the missing data the attacker would normally have to guess. By applying this mathematical filter, the required number of attacker guesses collapses from 256 down to exactly 1. Depending on how the runtime is measured, this optimization makes the attack between 200 and 800 times faster than the previous best attempts recorded by human academics. The machine formulated and refined the exploit in 3 days. It took the human researchers several hundred hours of study just to validate that the complex mathematical proofs were correct. the model engineered a completely novel mathematical filter to sever a recognized computational bottleneck. Following the HAWK and AES results, Anthropic expanded their testing, directing the model across a long tail of widely varying cryptographic protocols. This list tracks the subsequent tests. The lightweight encryption algorithm, or LEA-13, is a standard designed for low-power environments. Its previous best cryptanalysis required 2 to the power of 98 encrypted plaintexts. The model dropped that requirement to under 2 to the power of 30. This specific attack is highly practical. It can execute a full key recovery in under an hour on a standard modern desktop computer. The model then formulated another full key recovery attack against a 6-round variant of the Serpent 128 cipher. It proceeded to map out minor yet consistent efficiency gains against the Salsa 20 stream cipher. Finally, it identified algorithmic degradations in the Poseidon and SHA-1 hash functions. These exploits demonstrate a scalable, repeatable capability to analyze and systematically degrade a diverse set of cipher architectures. None of the attacks identified in these studies compromise any deployed real-world systems today. HAWK remains an undeployed candidate scheme, and the targeted version of AES is a reduced-round academic variant. Production software remains secure. This macro timeline illustrates an inversion in the cybersecurity workflow. The limitation in cryptography is no longer the time required to discover novel mathematical attacks. The machine operates in a matter of hours or days. The burden now rests entirely on verification. It takes human experts hundreds of hours, spanning months, to validate machine-generated proofs. Human cryptographers are now the rate-limiting step in global digital security. The models are rapidly scaling their ability to audit our defense structures. What happens when the next mathematical flaw they output lands on a primitive that is already active in production? For Synthetic Labs, from research paper to working prototype, keep building.